We will discuss about what causes change in membrane potential. There are two types of changes in membrane potential as we have discussed in the previous session. One is graded potential, which are local changes, and the other one is action potential, which is a rapid, transient, propagating change. Now, what will cause graded potential? There are two types of ion channels, gated ion channels, that are going to cause the graded potential. Those two types of gated ion channels are, one is ligand gated ion channel and two is mechanical gated ion channel. How these gated ion channels function? If we see a detailed diagram of these things, they exist in two states, in open configuration and closed configuration. They are composed of subunits, and the subunits are arranged in such a way they can either form hydrophilic tunnels which are open, or the hydrophilic tunnels can be closed. In closed configuration, the subunits are arranged in such a way that the ions cannot flow from one side of the membrane to other, but the tunnel is closed. In open configuration, they are arranged in such a way that they form a hydrophilic tunnel and the tunnel is open. Here the channel is closed. Okay, the tunnel is closed. And this is the structure in all the gated ion channels, ligand gated, mechanical gated, voltage gated. There are four types of ion channels, in which three are gated. These three are gated, and there is another type of ion channel called leaky ion channels. Leaky ion channels will be useful in maintaining resting membrane potential. They are not useful at all in this change in membrane potential. Only the ion channels which can make a change in membrane potential are these three: ligand gated, mechanical gated, voltage gated. Whereas these two, ligand gated and mechanical gated, cause the graded potential. How? Because if we say a mechanical gated ion channel. Mechanical gated ion channel responds to stimulus of pressure. Say if I touch or there is any pressure on my neuronal cell, that stimulus causes this mechanical gated ion channel to shift configurations. Generally it will be in closed configuration. Any stimulus given to that cell will shift the configuration from closed to open. When it shifts from closed to open, there will be ion flow. Depending on the ion, it will be either depolarizing or hyperpolarizing. Say if it is sodium ion will rush into the cell causing depolarizing potential. If it is potassium ion will rush out of the cell causing hyperpolarizing potential. If it is chloride ion will rush into the cell causing hyperpolarization. Okay. When it is ligand gated ion channel, the stimulus is a neurotransmitter. We generally observe this in dendrites, in the postsynaptic neuron. In the synapse, neurotransmitter in the synapse, from the presynaptic neuron, a neurotransmitter is released. This neurotransmitter interacts with the ligand gated ion channel and shifts the configuration of the ligand gated ion channel, or we can say ligand gated ion channel is activated. It shifts from closed configuration to open configuration. The same thing happens as in mechanical gated ion channels. Ions flow, making a change in membrane potential, either hyperpolarizing or depolarizing. Now, what is the difference between these two and voltage gated ion channel? These two will make a change in, or these two will induce graded potential, but this doesn't induce graded potential. Why? Because this will only open at a particular voltage. The stimulus for this is not pressure or neurotransmitter. The stimulus for this is voltage, and this will open at a particular voltage called threshold voltage. We have already observed this term in our previous class, and this is useful for generating action potential. Basically, these two channels will generate graded potential. If the graded potential reaches threshold voltage, that threshold voltage, at that particular point, at that threshold voltage, these voltage gated channels open, causing a rapid increase in influx of sodium ions. This rapid influx of sodium ions causes a rapid rise in membrane potential. Thus, rapid rise in membrane potential eventually causes action potential. So, we can say voltage gated ion channels causes action potentials. There are different types of voltage gated ion channels: potassium, sodium, and other things. Okay. Now, this voltage gated ion channel has three states: deactivated, activated, inactivated. It also exists in only these two configurations, closed and open, but we say it is in three states. That is, closed configuration has two states here. Number one state is deactivated. Generally, at rest, the voltage gated ion channel will be deactivated if there is no stimulus to this voltage gated ion channel. When there is a particular stimulus, that is the threshold stimulus which can induce threshold voltage. When the threshold voltage is reached, this voltage gated ion channel will shift from deactivated state to activated state. Eventually, when the membrane potential reaches a particular voltage, that activated state will shift from activated to inactivated state. Here, deactivated is closed, activated is open. When a particular voltage is reached, it shifts to activated, that is from closed configuration to open configuration. This shift from closed to open allows the rapid influx of ions. In general, in action potential, it allows the rapid influx of sodium ions if it is a voltage gated sodium channel. Eventually, membrane potential rises until a certain point, then the activated state shifts to inactivated state, or it becomes closed. For sodium, it is positive. For other ions, it may be other valency. So at a particular voltage, the activated shifts to inactivated state. Eventually, inactivated after a particular time, it shifts to deactivated states. There is a time period in which the inactivated state shifts to deactivated state. This time period from inactivated state to deactivated state is relative refractory period. We will discuss about relative refractory period in the next topic. Okay.